Hello. Today I have a very long video for you. We will be looking at the quantum mechanics for the double slit experiment. Electrons or other quantum particles are fired towards a barrier in which a pair of parallel slits have been cut. The resulting distribution of electrons found on a screen placed on the far side of the barrier depends on whether we have detected which of the slits, if any, the electron has passed through. If the detector is present, we get an essentially particle-like behaviour. When the detector is absent, we see an interference pattern associated with a wave-like description. This behaviour is retained even when the electrons are fired one at a time towards the barrier. In that case, we build up the pattern defined by the distribution of individual particle detection over a long period of time. There are a number of accounts of this phenomenon that lack the necessary rigour to describe this behaviour satisfactorily. It is not uncommon for presentations to use methods that are not well defined in the quantum theory in order to get the desired result. One example of this is to sum physical states, that is, ones defined only up to an arbitrary phase. The sum of two such states is not itself a physical state. The relative phases of the state is important in determining the interference pattern. These approaches typically neglect the description of the incident electron, which is what relates the phases of the two states corresponding to the passage through each slit. They also fail to describe the outgoing wave function in detail, and often somewhat ad hoc Gaussian wave functions are substituted for want of anything better. Our aim is to improve on these explanations. We will need to discuss the nature of the detector and the wave function collapse, or, more accurately, the decoherence due to the interaction with the environment that gives rise to these results. We will start our discussion with an explanation of density matrices. The quantum system is defined by a density matrix. This is a Hermitian completely positive linear map with unit trace. If the state of the system evolves according to the Schrödinger equation, then the density matrix ρ is the following, where psi of t obeys the Schrödinger equation. That is, IH bar d psi by dt is H psi. Therefore, the time evolution of the density matrix d rho by dt is d psi by dt psi plus that thing, and that's H over IH bar, that minus psi H over IH bar, the minus sign coming from the complex conjugate of the I there, and that's minus I over H bar, the commutator of the Hamiltonian with the density matrix, and this is the master equation. The pure state remains pure. If it was in this form, then over time it retains that form. It is psi of t. Psi of t. And therefore the entropy, S, defined to be minus k times trace of rho log rho. K is Boltzmann's constant. And that is 0. Let's consider a density matrix constructed from a pair of orthogonal states psi 1 and psi 2 in the following way. Rho equals P1 psi 1 with psi 1 plus P2 psi 2 with psi 2, where P1 plus P2 is equal to the trace of rho is 1, these being normalized states. This represents a probabilistic mixture of the two states. And in this case, the entropy we can calculate, and it will be minus k p1 log p1 minus k p2 log p2. And we could have a density matrix which represented a probabilistic mixture of an arbitrary number of states if we so choose. This thing is in general not zero unless the state is pure, which would correspond to P1 equal to 0 or P2 equal to 0 in this case. By using a density matrix formalism, we can allow pure states to evolve into mixed states, and that is the strength of using this formalism over the Schrödinger equation. Okay, suppose the total state of the quantum system and its environment is described by the density matrix rho total. If initially the environment and the system are non-interacting, this will be a tensor product. So at time 0, so that's the quantum system we're interested in. And that's everything else in the universe, that's the environment. Now suppose total Hamiltonian H is the Hamiltonian of the quantum system plus the Hamiltonian of the environment on its own plus H int, which is the interaction Hamiltonian. If H int was absent, that's 0, then we can involve this according to rho total is US rho S 0 US dagger tensor product UE rho E 0 rho E dagger, where US is the time order exponential minus I over h bar the integral 0 to t hs of t prime dt prime, and UE is the time order exponential of the environment Hamiltonian. That's going to be to e to the minus I hst over h bar, and that's e to the minus I het over h bar if hs and he are independent of time. However, if h int is not 0, then there is interaction between the system and its environment, and the simple tensor product form is no longer preserved. In general, the quantum system will interact with its environment and become entangled, which means that as far as a state description goes, the total state is not simply the state of the system tensor product, the state of the environment. So we have an entangled state, and then for an entangled state the evolution does not obey this rule. Now let's ask the question, what does the evolution of the system look like if we do not have access to the quantum state of the environment. We can derive this by taking the partial trace of the degrees of freedom in the environment. This leads to a new evolution equation for the density matrix of the system. What we find is that the master equation, which is this equation here, is modified. It takes the form that's the original form, but we get some extra terms, which is the sum over an arbitrary collection of indices, L alpha rho s L alpha dagger minus a half rho s L alpha dagger L alpha. And this is the Lindblad form of the master equation. If you were to take the trace of both sides, you'll see that the d by dt of the trace of rho s is 0 by the cyclic property of the trace. The effect of the new terms is to encapsulate how the entanglement with the environment and the subsequent discarding of the information transferred into the environment takes a pure state of the system into a mixed one. Now, we have made certain physical assumptions, and that is that the rate of change of the density matrix depends on the density matrix at the current time. This is a Markovian approximation. In this approach, the wave function never collapses. The overall state of the universe evolves according to a unitary description. It is through the interaction of the quantum system with its environment and by discarding the information passed to the environment that perceived wave function collapse occurs. This has a close relationship to the relative state formulation of quantum mechanics, which is popularly known as the many worlds interpretation, though it is not a name I particularly like. Let's now summarize the quantum mechanical system we will be examining. We will take a barrier. We're going to write that as z equals 0, and an emitter of electrons. We fire the electrons towards the barrier. On the other side we have a screen. We'll have this at z0, which is going to be less than 0. This is the z direction. And this is z1, location of the screen. This we will take to be the x direction, and the y direction is orthogonal to the paper. We will consider two situations. One in which there is a detector which detects whether the electron has passed through the upper slit. So we'll call this distance A. That's also A. 2 epsilon will be the width of the slits. We need to understand the detector. This might be a light shining at the slit with a sensor detecting whether an electron has scattered the light. Close-up of the barrier might look something like this. We're going to call this region here X. We can define Px to be the projection onto x. So we can write it like that and let x bar be all of three-dimensional space without the barrier and without x. So px plus px bar is equal to everything, because we're only going to be defining our wave function on the space with the barrier removed. Px squared, being a projection, is just px. And similarly, px bar squared is px bar, and they're orthogonal as well. Px bar is px bar px is from 0. Now let's take a Lindblad operator, which is root gamma times the projection onto x. And we'll consider a Hamiltonian H. For simplicity, I'll write it as v dot p. It won't be the one we'll be interested in. We'll be interested in the free particle Hamiltonian, but this will give us an idea of how the Lindblad operator affects the evolution of the density matrix. So we'll take v to be v times the vector k, with v greater than 0. And let x be 0, 1 cross r cross 0, 1. So in this case we're going to be looking at a region like that, and it extends infinitely far upwards and downwards into the plane of the paper. Let rho of 0 be psi pure state, such that psi is equal to root p a plus root q b, where p plus q is 1 a, b are normalized states. Sharply peaked at A and B. So they could be Gaussian. Ideally I'd make them position eigenstates, but if I do, then they would not be normalizable. So instead I'd make them Gaussian, concentrated at A and B. We'll start off with A being here and B being up here. So perhaps A can be a half naught minus 1. So that's naught, that's 1, that's a half. B will have as 2 naught minus 1. Now we wish to solve the equation d rho by dt is minus I over h bar, the commutator, plus gamma p rho px minus a half px rho minus a half rho px. This is just the Lindblad form. And I have dropped the subscript s from rho and from h. Well, I can write that as the following. That's the identity on the other side, which I can write as px plus px bar. px plus px bar rho px that term and that term cancels out with that term. There's a minus sign missing there. Minus I over h bar, h with rho, minus a half gamma px bar rho px plus, we've got the half px rho px bar. Okay, let at be e to the minus iht over h bar times a, and that's e to the minus iv dot pt over h bar a, which is just the translation operator with parameter vt acting on the original state, which is why I chose the Hamiltonian to be of the form that I did to make this calculation easy. Let's try and solve it by taking rho of t to be alpha of t times at plus beta of t bt defined in the same way as I did for at, and then we have at bt plus bt at. Initially, alpha of naught is p, beta of naught is q, and gamma of naught is the square root of pq. That comes from this and this. Well, let's substitute this into the master equation. d rho by dt is minus I over h bar times alpha. If I apply the time derivative of this from here, that brings down minus I over h bar, so that's an I over h bar, h times this whole thing again, so that's at times at. We have minus that, the minus sign coming from the fact that one's taking the dagger of this to get the bra rather than the cat, plus beta over IH bar BT H there, minus beta over IH bar BT H, plus gamma times H over IH bar ATB T minus H over IH bar AT, the H is in the wrong place there, BTH, plus the Hermitian conjugate terms. And I also need to differentiate these things as well. Alpha dot AT plus beta dot BT plus gamma dot ATBT plus BTAT. And this is minus I, sorry, that wasn't there. I was just differentiating this, but that gives me the commutator of H with rho in those terms here, plus alpha dot AT plus beta dot BT plus gamma dot AT BT plus BT AT. Now compare that with the Lindblad form of the master equation. It's got to be that commutator of H with rho minus a half gamma px bar rho px plus px rho px bar. That's minus I over h bar commutator of h with rho minus a half gamma, little gamma, times the indicator function that at is in x times at bt plus bt at. So this term is only ever zero when one of the particles has entered x and the other one hasn't. So that's what we find. Okay, well that means that this thing is equal to this thing, and therefore alpha of t is equal to alpha of 0 is p, beta of t is equal to q, and gamma dot is minus a half gamma little gamma times the indicator function. So this corresponds to exponential decay when the particle AT is in the detector. In other words, gamma of t is equal to square root of pq if Vt is smaller than 1, square root of pq e to the minus gamma Vt minus 1 over 2v if 1 is less than Vt is less than 2, or root pq e to the minus gamma over 2v if Vt is greater than 2. Thus, if gamma over v is large, then after A of t has passed through the detector, gamma of t is basically 0 to an excellent approximation, and the density matrix is therefore P times AT plus Q times BT. In other words, the pure state has evolved into a mixed state defined by two non-interfering quantum states corresponding to the part of the original state passing through the detector and that part which does not. So after passing through the detector, we have almost complete decoherence. Now, if I were to write psi of t equal to root p a of t plus root q b of t, so this is the evolution of the state in the absence of the detector, then we found that rho, when we do have the detector, is given by the following. Where psi x is the projection onto x of the state. Psi x bar is the projection onto its complement. Now this thing can be written as p times psi x with psi x over psi x, that's using the p x squared is px, and actually px dagger is px. Plus q times the same thing with x replaced by its complement. And P here can be written as psi x with psi x, which is also psi x with psi over the square root of psi x with psi x squared. And Q is the same thing with x replaced by x bar. And this is the usual von Neumann rule for the collapse of the wave function. In effect, the measurement has forced the pure state into a mixed state with the usual probabilities. We want to apply these ideas for the free particle Hamiltonian H is p squared over 2m instead of our toy model that we just used. Our state will be a Gaussian wave packet with average speed v moving towards the detector. A detailed description of how the detector works is beyond the scope of this video, but it might be best explained in terms of the dynamics of a quantum stochastic system. Let us now look at the free electron. So we model the quantum mechanics of the electron in a non-relativistic limit. Our system does not depend on spin, so we omit the electron spin state. The free particle Hamiltonian is given by that, put a hat on it to emphasize that's the operator. Momentum eigenstate P has a wave function determined by this calculation. So I've used the rule that for a wave function we can define the momentum operator acts on wave function by minus I h bar times the gradient. And therefore x with p is some constants times e to the ip dot x over h bar. And we want to normalize these states by the condition that delta cubed x minus x prime, these are all in 3 dimensions, is x and x primed, and that's the integral of x primed with p, p with x d3p. So that's modulus of c squared times the integral of e to the ip dot x minus x prime over h bar d3p, and that's 2 pi h bar cubed mod c squared delta cubed x minus x prime, a standard result in the theory of distributions. So x with p is e to the ip dot x over h bar divided by 2 pi h bar to the 3 over 2. Now the time evolution operator u of t is e to the minus I h t over h bar is e to the minus ip hat squared t over 2m h bar. Then a state evolves according to the following rule. So the wave function is going to be the integral x with p, p with e to the minus ip hat squared t over 2m h bar psi 0 d3p. 1 over 2 pi h bar to the 3 over 2 times the integral e to the minus ip squared t over 2m h bar plus ip dot x over h bar p p with psi naught d3p. So this expresses it in terms of the momentum representation of the initial state. We're going to take an initial Gaussian wave packet in the momentum representation as the following: tau over m pi h bar to the 3/4 e to the minus ip dot x naught over h bar e to the minus p minus mv squared tau over m 2m h bar. This is normalized since psi naught with psi naught tau over m pi h bar to 3/2. The integral, that's of course when you put the complex conjugate in, will cancel off with itself, so get e to the minus p minus mv squared tau over m h bar d3p, and we're integrating a Gaussian, so we end up with tau over m pi h bar 3/2, we get a pi m h bar over tau to 3/2 is 1. Now if we want to, we can use this expression here to work out what the wave function of the free electron is. I'll write down the answer, but I won't go through the calculation because we're going to be doing something rather similar to the calculation later on in the video. So get e to the minus mx minus x naught minus vt squared over 2h bar tau plus it minus imx minus x naught dot v over h bar minus imv squared t over 2 h bar. So we can see that x naught is the location of the electron at t equals 0. The Gaussian evolves into a new Gaussian, but different parts of the wave function move at different speeds, and therefore we have dispersion. Initially we find that delta xi delta pj is a half h bar at t equals 0. It's a simple calculation best done in momentum space, and so it's a minimum uncertainty wave packet. And as I say, initially the Gaussian is centered at x equals x naught, and for all time the expectation of the momentum is v over m. Okay, next we're going to look at the Green's function. So we had u, the evolution operator, and let's work out following matrix element. That's integral of x u of t p p x prime d3 x prime p prime, and that's 1 over 2 pi h bar cubed the integral of e to the I p x minus x prime over h prime. There's a dot in there. E to the minus ip squared t over 2m h bar d3p. So I've used u is e to the minus ip hat squared t over 2m h bar That's a momentum eigenspace. That gives that term. And then I've got two terms which are inner products of p with x primed and x prime with p, and that gives this factor outside and this exponential here. Okay, well, I can complete the square and I'll get e to the imx minus x prime squared over 2h bar t over 2 pi h bar cubed. The integral of e to the minus ip minus m x minus x prime divided by t, all squared divided by 2mh bar d3p, and that's e to the imx minus x prime squared over 2h bar t divided by 2 pi I h bar t over m, all to the power 3 over 2. So I'm going to write that as g of x minus x prime and t. And at t equals 0, we have got this divided by 0, so I want to think about that a little more. Well, x with psi of t that's x with u x primed psi naught d3 x prime. That's g of x minus x prime at t times psi of naught in a product with x prime d3 x prime. And so that's for t greater than 0. If we were to put t equal to 0 in this equation, then you would see that g of x minus x prime t would just be delta cubed x minus x prime. Okay. If t is greater than 0, partial derivative of g of x minus x prime t dt is x with the time derivative of u acting on that. We're just taking the time derivative inside the inner product. Remember, x and x primed are position eigenstates and don't depend on time. U was e to the minus iht over h bar. So that's hu over ih bar x prime. But h was p squared over 2m. And so that gives me ih bar over 2m del squared of x u x primed. ih bar over 2m del squared g of x minus x primed at time t. Now, if psi of x and t is a solution to the Schrödinger equation, then we have, I think this is x primed there, and I'll just rewrite what I've got here. G x minus x prime dt is ih bar over 2m del prime squared g x minus x prime d. I'm using the fact that this is even in x minus x prime. Next, I'm going to define the convolution of two functions f and g to be the integral 0 to t f of s g of t minus s ds. By a change of variables, s goes to t minus s, that's following. Now this is really the convolution you get from considering the Laplace transforms. So we would tend to think of f and g being 0 for t less than 0. Okay, well let I be f primed star g minus f star g primed, where primed is just derivative with respect to its argument. That's the integral 0 to t of f primed of s g of t minus s minus f of t minus s g primed of s ds. And that's the integral 0 to t total derivative with respect to s of f of s g of t minus s minus f of t minus s g of s ds plus the integral 0 to t f of s g prime of t minus s minus g of s f prime of t minus s ds. There's a relative minus sign which has come around because we're differentiating with respect to s, but prime means differentiation with respect to the argument of the function. That's f of s g of t minus s minus f of t minus s g of s between 0 and t. And this thing is just what we started up with. So move that to the other side and we'll find f g prime minus g f prime is g of t f of 0 minus f of t g of 0. Okay, so that was just an aside on convolutions. So what I'm going to do is apply this with little g being equal to big G here and f being equal to psi. So what we find is that delta cubed x minus x prime, that of course is g at time 0, psi of x prime and t minus psi of x prime at time 0 times g of x minus x prime t is up to minus I h bar over 2m into psi x primed t convolution with the derivative gradient squared g of x minus x primed t minus g of x minus x primed t convolution with del prime squared psi of x primed and t. And that's equal to minus I h bar over 2m divergence of psi x prime t star grad primed g of x minus x prime t minus g of x minus x prime t convolution gradient primed psi x prime t. So the convolution is with respect to time. Okay, let V be the set of x, the coordinates x, y, z, such that z is less than 0. So if you remember our setup, there is z0, z equals 0. So this region is V. And that region we're going to take to be V bar in a second. let us define x tilde to be xy minus z if x is x, y, z. So it's just reflection in the barrier. Let the Dirichlet-Green's function gd be g of x minus x prime times t minus g of x tilde minus x prime. There's no d on there. So in particular, gd of x and x prime t is 0 if z primed is 0, because the g of x, y, z and t is equal to g of x, y minus z and t. Okay, so we can take this expression that I've already got and substitute for the Dirichlet-Green's function. That's if x is in V. If x is not in V, then gd of x and x prime at 0 is delta cubed x minus x prime minus delta cubed x minus x tilde minus x prime. But that's in V bar. So this applies if x prime is also in V. So what I can do is integrate this over all of V. And what we find is psi of x and t is the integral over b of g dx and x primed t psi of x primed at 0 d3 x primed minus I h bar over 2m, the integral over the boundary using the divergence theorem, the psi of x primed t convolution grad primed g Dirichlet-Green's function t dot ds primed, provided that the boundary term goes to 0. That's order 1 over mod x squared, as mod x goes to infinity. And we also need psi of x falls off fast enough. Well, I'm going to apply it with psi being a Gaussian, so these conditions are going to be satisfied very easily. Notice we use that gd vanished on the part of the boundary given by the barrier. Now ds prime dot grad g dx x prime of t, there's our barrier, that's B. So that's the outward pointing normal to the barrier, which will be in the direction 0, 0, 1. So that's minus 2 ds prime dot gradient of g of x minus x prime t. That's a plus. Actually, the minus sign is correct, as I have replaced the gradient with respect to x primed by the gradient with respect to x. This will just change the overall sign of the wave function that we calculate and does not change the probability densities we will be computing. So psi of x and t is the integral over v of g dx and x primed at time t is like 0 d3 x prime minus I h bar over m, the integral over the boundary of v times the gradient psi, that's with respect to x now. And this formula allows us to find a solution inside the domain V. So we have our initial Gaussian. This goes here. We might have some slits here. If we were to have the boundary condition that the wave function vanishes on here, then we get total reflection. And we can see that if this thing vanishes, then we just get psi of x and t is phi of x and t minus phi of x tilde and t, where phi is a solution in the absence of the boundary. And this corresponds to the method of images. Now what about v bar? If we're over here, then we can do the same calculation, except this delta cubed x minus x prime will have to have a minus delta cubed x minus x prime, that's a tilde in there as well. And therefore we end up with minus psi x tilde of t is the integral over v bar, Dirichlet-Green's function, psi of x prime 0 d3 x prime, plus I h bar over m, integral over the boundary grad, that's with respect to x, of psi of x prime t convolution with g of x minus x tilde, that's primed, dot ds. The relative sign change here comes from the normal to that is minus the normal to the boundary of V. Okay, let's use this to work out the wave function that we get when we fire an electron at a single slit. So that distance A, that is 2 epsilon. The wave function x with psi is equal to 1 over m, the integral 0 to t dt prime dx prime dy prime x with pz hat is minus I h bar times the gradient, or d by dz, when acting on wave functions. U t minus t primed x primed y primed 0 x prime y prime 0 u of t primed psi 0. So what I've done here is I'm going to assume that initially psi is 0 in the region V bar, so we get nothing from there. That minus sign has come over, so you get a minus h bar gradient, that's the pz. And I'm going to assume that on the barrier, psi is 0 here and here, and on this part it's going to be given by the value that you get from just evolving the Gaussian wave function up to the barrier. That explains why we get the integral dx dy of this thing here. Now, x will go from a minus epsilon to a plus epsilon, y from minus infinity to infinity, so we're considering an infinite slit. Well, that's equal to 1 over m, the integral 0 to t dt prime, integral dx prime dy prime, integral d3p prime, integral d3p double prime of p with pz hat u t minus t prime. Well, actually, I'm going to try and do the calculation to start with in momentum space. So instead of x, we're going to get p here. It just turns out to be a little bit easier to do it this way. X prime y prime 0, x y 0, p prime u of t prime psi of 0. Okay, so this was dealing with the convolution. What's happening is that we are evolving the state up to the barrier at time t primed. Thereafter, we are applying the restriction to the slit. That's what this integral here is doing. And then we're evolving. So we're using that as the initial condition, if you like, for the wave function on this boundary. Then in the region V bar, if we are evolving this into this region with a time t minus t primed. Well, that's 1 over m times 2 over m pi h bar to 3 over 4. That comes from substitution for p primed with psi of 0. Obviously, u is a function of the momentum operators, so it's rather easy to act on the momentum eigenstates. We have the integral 0 to t primed dt prime, or 0 to t dt prime, so that's the convolution going in, dx prime and dy prime, a minus epsilon to a plus epsilon. We have the d3 primed and d3 double primed of p with p z hat u of t minus t prime, p double primed, p actually I've already written that, so let me not write that. This pz z hat acting on this just gives a pz. Okay, e to minus p squared t minus t prime over 2m h bar, that's u acting on that thing, and we get the inner product of p with p double prime, which gives delta cubed p minus p double prime. Then we get these terms here, which give us e to the I p x primed minus p x double prime x over h bar, e to the I py prime minus py double primed y over h bar divided by 2 pi h bar cubed. There's an e to the I pz primed pz double primed times not z but 0, so that term doesn't appear, times e to the minus I p prime squared t primed over 2m h bar. That comes from that p primed and that u, e to the minus px prime squared plus py prime squared plus pz prime minus mv squared 2 over 2m h bar, e to the minus I pz prime z naught over h bar. This term, of course, just comes from psi of 0 in the momentum space representation. Okay, we can do the delta function integral. What we will find is 1 over m 2 over 16m pi to the 5 h to the 5 to the 3/4 integral 0 to t dt prime integral dx a minus epsilon to a plus epsilon integral dy minus infinity to infinity integral d3p prime of pz e to the minus ip squared t minus t prime over 2m h bar e to the I px prime minus px x prime over h bar. Those should have primes on them, by the way. They corresponded to those things there. E to the I p squared minus p prime squared t primed over 2m h bar times e to the minus px squared primed plus py prime squared plus pz primed minus mv squared 2 over 2m h bar and an e to the minus ipz primed z naught over h bar. Those should have primes on them as well. Okay, we need to do some of these integrals. Well, the integral a minus epsilon to a plus epsilon dx prime and dy prime of e to the I px prime minus px x prime over h bar plus I py prime minus py y primed over h bar times e to the I p squared minus p prime squared t primed over 2m h bar is, we can do the y integral very easily because we'll get 2 pi h bar delta py minus py prime, leaving me with this integral and I'll write this thing out explicitly. That's px squared minus px prime squared plus pz squared minus pz prime squared t prime over 2m h bar. I've used, of course, that py and pz have to be the same thing in that case. Now I can do this integral in x, so that's going to give me 4 pi h bar squared sine of px prime minus px epsilon over h bar divided by px prime minus px times this delta function that we had for py and y prime. And we have an e to the I px minus px prime a over h bar. So that came from doing the x integral that we have there. The two differences between minus and plus epsilon were combined to give the sign. And we still have an e to the I px squared minus px prime squared plus pz squared minus pz prime squared t prime divided by 2m h bar. Now we'll need to do the pz prime integral in this expression, and what will be useful is to notice that the integral of e to the minus az minus z naught squared minus bz squared plus 2cz, that's the integral. This is from minus infinity to infinity, a plus b into z minus az naught plus c over a plus b, all squared dz times the exponential e to the minus az naught squared plus az naught plus c all squared divided by a plus b. So we do that by completing the square. That's equal to square root of pi over a plus b e to the minus a b z naught squared plus c squared plus 2c a z naught all over a plus b. So using this result, we get that the integral dpz primed of e to the minus ipz prime squared t primed over 2m h bar, that was from that part. We also had pz primed in here and here. E to the minus pz primed minus mv squared over 2m h bar minus ipz primed z naught over h bar. Apply this rule, that's root 2m pi h bar over tau plus it prime e to the minus mv squared tau over 2h bar times e to the m v tau minus iz naught squared divided by 2h bar tau plus it prime. So putting some of these stuff together, we have dpz prime integral a to minus epsilon a plus epsilon dx primed, the dy primed integral of e to the I px prime minus px x primed over h bar plus I py primed on there actually, y primed over h bar e to the I p squared minus p prime squared t primed over 2m h bar e to the minus m v squared tau over 2h bar e to the m v tau minus iz naught squared over 2h bar tau plus I t primed actually no, I've jumped ahead. Let me put in the minus pz primed minus mv squared tau over 2m h bar e to the I minus I p z primed z naught over h bar is equal to square root of 32m pi cubed h bar to the 5 over tau plus I t prime, sine of px prime minus px epsilon over h bar divided by px prime minus px delta of py minus py prime e to the minus ipx minus px prime a over h bar e to the ipx squared minus px prime squared plus pz squared t prime over 2m h bar, and then we get e to the minus mv squared tau over 2 h bar e to the mv tau minus iz naught squared over 2 h bar tau plus I t primed. We can do something with this last term here. That's the same thing as e to the minus imv squared tau t prime plus 2z naught v tau plus z naught squared over 2 h bar tau plus I t primed. Just connecting all of these things together. We can do the integral over the delta function so that the py integral, so of all of that, actually let's write it in full. dy minus infinity to infinity e to the ipx prime minus px x prime over h bar plus the same thing in y e to the ip squared p prime squared t primed over 2m h bar times e to the minus pz prime minus mv squared tau over 2m h bar minus I pz prime z naught over h bar e to the minus py prime squared tau over 2m h bar. That's equal to the square root of 32m pi cubed h bar to the 5 divided by tau plus it prime, the sine px prime minus px sine over h bar px prime minus px e to the minus py squared tau over 2m h bar e to the minus ipx minus px primed a over h bar e to the ipx squared minus px prime squared plus pz squared t prime over 2m h bar times e to the minus m z naught plus b t primed squared over 2 h bar tau plus I t prime e to the minus mv squared t primed over 2 h bar e to the minus I mv z naught over h bar. So here I was able to simplify this equation by completing the square. Now let's multiply by 1 over 2 pi h bar to the 3 over 2 e to the I xpx plus ypy plus zpz over h bar, that will turn the momentum space representation into an ordinary wave function configuration space. But we also, when we were going through here, so far we haven't taken account of the fact that this u has an exponential of e to the minus ip squared t minus t prime. I've been concentrating on the t prime dependence. Now we put this term back in. And I'll write it out in components. And then I'm going to integrate with respect to py. And we're going to use the result that the integral dpy of e to the minus py squared tau plus it over 2m h bar e to the ipyy over h bar. Just complete the square, or use that result I wrote down earlier. Tau plus it e to the minus my squared over 2h bar tau plus it. We'd also like to do an integral with respect to pz. The integral dpz, if we collect together all the pz terms that are in our calculation, we have a pz outside minus I pz squared t minus t prime divided by 2h bar e to the I pzz over h bar. Now this is a little bit tricky because this thing actually diverges. You can make sense of it as a distributional result, or we can just use the fact that pz has a representation of minus ih bar d by dz and use that and then apply that to the integral. And in fact, this is where it came from in the first place, so we're really just undoing something we didn't need to do. And that's minus ih bar d by dz of root 2 m pi h bar over t minus t prime e to the minus I pi by 4 for the 1 over the square root of I e to the I mz squared over 2h bar t minus t primed. And that gives me mz over t minus t prime to the 3 over 2 times the root 2 m pi h bar e to the minus I pi by 4 e to the I mz squared over 2h bar t minus t prime. Next, let us deal with the dpx primed integrals. So this is a little bit more tricky because of the px prime minus px in the denominator. Now the numerator also vanishes, but it's still not so nice. So let me write IA. The thing we need to integrate is this thing from minus infinity to infinity in both cases. So p prime minus p epsilon over h bar, p prime minus p. So I've dropped the subscript x just for notational convenience. E to the I p prime squared over 2m h bar e to the minus I p prime squared tau over 2m h bar. then differentiate that with respect to A, and we'll get I over h bar integral dp dp prime sine p prime minus p sine over h bar. So that brought down a factor of p minus p prime, which cancels with that. The I minus I came down in the denominator, so that gives me that thing. We still have an e to the minus I p prime minus p a over h bar e to the I p x over h bar e to the minus I p squared t minus t prime 2m h bar e to the minus p prime squared 2 plus I t prime over 2m h bar, and that's 2 over h bar dp dp prime I p prime minus p a minus epsilon over h bar a plus epsilon over h bar. Of course, that's how the sign came in the first place, so I'm just writing the sign in terms of complex exponentials. And we have all of this stuff again. There we go. And that's 4 pi m over 2 plus I t prime to the 1/2 t minus t prime to the 1/2 times e to the minus m a minus epsilon squared over 2 h bar 2 plus I t prime plus I m x minus a plus epsilon squared over 2h bar t minus t prime minus the same, but with epsilon goes to minus epsilon. And we did that just by repeatedly doing the p and p primed integrals. They were just Gaussian as usual. Now we know that IA goes to 0 as a goes to plus or minus infinity. That's obvious from physical grounds. This integral was part of the formula for the wave function. If that distance is a and then we send that off to infinity or minus infinity for a Gaussian starting here, this term should go to 0. It also follows from the Riemann-Lebesgue lemma. For a mathematical justification. Now I want to complete the square on this, so let's examine minus m. Before I do that, let's just say that I of a then is 4 pi m over 2 plus I t prime to the 1/2 t minus t prime to the 1/2 integral a to infinity v to the minus m alpha plus epsilon squared over 2h bar 2 plus I t prime plus I m x minus alpha minus epsilon squared over 2h bar t minus t prime. So that just comes from sticking an integral and integrating from a to infinity, and of course there's a minus sign because we've got the lower limit in there, so that's why I'm writing the one with epsilon goes to minus epsilon first. And so epsilon goes to minus epsilon in there. Now I can rewrite this minus m alpha plus epsilon squared over 2h bar tau plus it prime plus mx minus alpha minus epsilon squared over 2h bar t minus t prime is collecting all of the coefficients of alpha plus epsilon squared and putting them over a common denominator. Gives me that thing. So we get alpha plus epsilon. Then we get a term corresponding to the cross term in x, and that's minus x plus I t minus t prime x over tau plus I t squared. So that gives that term. I get a term which I don't want. That cancels off the term I get from squaring that term there, and then this term corresponds to the term I do want from the x squared term there, and I'm missing an I in there, so that works. So that's I m tau plus I t over 2 t prime. There should be an h bar there. T minus t prime into alpha plus epsilon minus x plus I t minus t prime x over tau plus I t all squared. And combining these two gives me minus mx squared over 2h bar tau plus I t, and that is it. So IA is collecting all of these together, and by change of variable you get 2 to the 3 over 2 pi to the 3 over 2 m to the 1/2 tau plus I t to the minus a half e to the minus I pi by 4 e to the minus mx squared over 2h bar tau plus I t times the complementary error function of m to the 1/2 e to the minus I pi by 4 tau plus I t to the 1/2 divided by 2 to the 1/2 h bar to the 1/2 tau plus I t prime to the 1/2 t minus t prime to the 1/2 times a plus epsilon minus x plus I t minus t prime x divided by tau plus I t minus c. That is, epsilon goes to minus epsilon in there. So I've used the fact that the complementary error function is of any number z is 2 over root pi integral z to infinity e to the minus u squared du. So this lets us work out the wave function. So putting all of this together, we finally get the wave function in the exterior region. So this is for x in v bar is minus I 4 tau to the 3 m to the 5 over pi to the 5 h bar to the 5 to the quarter. That's just collecting all the coefficients together. Z e to the minus I mv z naught over h bar e to the minus mx squared plus y squared over 2h bar tau plus it times the integral dt prime naught to t over e to the minus mz naught plus vt prime squared over 2h bar tor plus it primed minus imv squared t primed over 2h bar plus imz squared over 2h bar t minus t primed, all divided by t minus t primed to 3 over 2 now, tor plus it primed to 1/2 times the error function. This is still part of the integral, m to the 1/2 e to the minus I pi by 4, tor plus it to the 1/2 divided by 2 to the 1/2 h bar to the 1/2 tor plus it primed to the 1/2 t minus t prime to the 1/2 into a plus epsilon minus x plus it minus t primed x over tor plus it minus the elementary error function of the same thing with epsilon goes to minus epsilon. Okay, so that's our final wave function. Now, that it'd be pretty hopeless to try and do the integral with the t primes distributed as they are. You can just about do the integral in the case that epsilon goes to infinity and then you lose the barrier entirely and you'll just get the free particle wave function back again. Up to the other term that you have, which was the integral which corresponded to this thing here. Okay, now let's consider the double slit. So we approximate the distribution on the screen by setting t equals t naught, where t naught is z minus z naught over v. This is the classical time at which the electron would have hit the screen. For a pair of slits, if the slit at A has x part of wave function, the thing I was calling I of A, I'm going to write that as I sub A now, and psi, let's call this psi of x. I'll write psi of x is psi sub A to distinguish it from psi of minus A, which is for the slit when it's located around minus A. So the relative probability of finding the electron in the case where we have the detector is going to be x with psi A squared plus x with psi minus A squared. It's a good approximation. This is when the density matrix no longer corresponds to a pure quantum state and we have a superposition of two states which no longer interact with each other. That is when we have decoherence, corresponding to the particle going through one hole or the other. There's actually quite a lot of possibility that the electron will bounce off the barrier entirely. That does not contribute to the wave function to the right of the barrier. For no detector, the probability will be x with psi A plus x with psi of minus A all squared by the linearity of the Schrödinger equation. On the screen is a graph showing the probability density for the electron after it has passed the barrier. In blue is the case where there is no detector, and you can see you get some interference with the oscillations, and the oscillations illustrates the interference pattern. If there is a detector, we get the yellow graph, which shows there is no interference. We do, however, get a bit of diffraction occurring, and that explains why it's spread out rather than a fine line in the direction going from the source to the screen. So this gives an intensity which is roughly like that in the case for the detector, and it will be oscillating like that in the case where we have no detector. So we can plot this as an intensity diagram, and this is the sort of thing you would see if you to actually perform the experiment. So at the top diagram on the screen is the result if a detector is placed at one of the holes. The lower diagram shows what happens if there is no detector. Okay, well that completes our calculation. Let us now address the ways in which we might improve the calculation. Firstly, we use the non-relativistic Schrödinger equation for an electron rather than the Dirac equation. Since we're only dealing with low energy electrons, this approximation is fine. An analysis using the Dirac equation could be performed if we chose to do so, though the calculation with spinors and Dirac matrices would make it significantly more complicated than the one we have performed here. We also chose to consider a single electron rather than a multi-particle system of electrons. This can easily be accounted for. The electron is a fermion and the total multi-particle state will be totally antisymmetric. This includes the spin components. Our states, which exist in a tensor product of a number of copies of the rigged Hilbert space, would have a spatial component that is either totally symmetric or totally antisymmetric, and a spin component built up from totally symmetric or antisymmetric total spin eigenstates. However, the interesting part of the calculation is exactly what we have presented here. The analysis for the double slit experiment for light would look somewhat different. There is no wave function for light, at least not in the conventional quantum theory, although there do exist some interesting attempts to formulate such a quantity. Instead, we look at the quantization of the electromagnetic field and construct coherent states from the annihilation and creation operators of the field expansion. Since light is by definition ultra-relativistic, the formulation that we have used here, using a non-relativistic Schrödinger equation, would clearly be incorrect, and the calculation would look rather different, although the resulting images are extremely similar. And that concludes a quantum mechanical description of the double slit experiment.